Good afternoon, everybody. My name is Alexander, and this is Maya. And we both work at Facebook in data infrastructure team for developing highly scaled distributed algorithms. So today, we're going to talk about large-scale collaborative filtering implementation that we did on top of Apache Giraph. So we're going to start by briefly introducing Giraph. This is a very powerful platform that we often use in Facebook for complex data analysis. And then we're going to focus on collaborative filtering. We are going to describe the problem in details, describe some of the challenges that we needed to resolve in order to handle massive Facebook data. And then we're going to talk more about two approaches that this problem is commonly solved. And from this point, we're going to be more technical. In particular, we are going to explain also applications that we have in Facebook and compare our results with Hive and Spark implementations as well. And finally, we're going to conclude at the end.
So Apache Giraph is a large-scale, highly performant platform for doing graph processing and, in general, any kind of iterative processing. It can handle massive data sets. For us at Facebook, that means over 1 billion vertices and up to 1 trillion connections. Giraph operates on graphs, and problems that are not necessarily graph problems need to be mapped to a graph in some way using primitives that Giraph provides. And these primitives are vertex IDs and values, as well as edges and values associated to them. And depending on the application, vertex values and edge values can hold any kind of data. One simple example would be vertices could be Facebook users, and vertex data could be some information about these users, for example, their favorite color. Edges could be friendships on Facebook, and edge values, strengths of these friendships. When writing Giraph applications, we think like a vertex, meaning that at any point of the algorithm, we write what a vertex should do. How should it modify its value, edges, which messages it wants to send to other vertices in a graph, and how to consume messages it received from others. Giraph runs on top of Hadoop. It is compatible with multiple Hadoop versions, and at Facebook, we run it on top of Corona, which is our internal implementation of Hadoop. Giraph jobs are map-only jobs, and we mostly use Hadoop just as resource manager and scheduler. Even though it runs on top of MapReduce, it follows quite a different model where it loads all the data in memory in the beginning of the job and keeps it there, allowing you to iterate through data as many times as you'd like. This way, it avoids slow reads and writes from the disk after and before each MapReduce stage. And since we don't communicate through the disk anymore, we directly communicate through the network. I'll give you just a basic overview of Giraph Workflow, and then we'll dig into collaborative filtering. So in Giraph, we have a set of machines that you want to use to run your job on. We call them workers, and your graph gets automatically distributed across these machines. Once the data is there, the computation starts. Computation consists of a certain number of iterations that we call supersteps. And in each of these iterations, vertices do some kind of local computation. They can modify their value and edges, and they can send messages to other vertices in a graph. After all the vertices have done the computation, there is a global barrier ensuring that all the messages have been delivered, and the next superstep starts. And then in the next superstep, vertices can consume the messages they received. They can send new messages, modify their value, and so on. This is just the basic overview of how Giraph works. There are many features that we added to it over time to support different use cases, and we'll talk about some things that we added specifically for collaborative filtering later on.
OK, so let's now describe the problem that we are actually trying to solve here, which is collaborative filtering. So collaborative filtering is a technique for predicting user interest that is based just on the interest on all other users. In other words, collaborative filtering is based on the idea that the best recommendations for a particular user come from users that are like-minded. So this became particularly popular after the Netflix $1 million competition, where the main goal was to develop an algorithm that would predict user ratings for a certain set of movies just based on the previous ratings that this user made. But this can be applied on other things as well. For example, recommending pages you might like at Facebook. So assume that Maya likes these 4 Facebook pages, Disney, roller coasters, Disneyland, and Six Flags. And I like Disney and roller coasters. So if we have just this information, ignoring completely other features that we might use here, for example, like age and country, and the fact that I'm terrified of the roller coasters, we can actually, it's likely that I will like the other 2 pages, Disneyland and Six Flags. And I can get the following recommendation on my Facebook page. So the main challenge that we have here for designing the algorithms that will work on Facebook data is how to scale this problem to our size. So here we are talking about more than 1 billion users and millions of items. So the largest numbers that anyone ever talked on this field are at least 2 orders of magnitude lower. For example, that Netflix prize competition, so the data set there was 100 million ratings, and we are dealing here with 100 billion ratings. There are other problems with Facebook data sets as well. For example, we have really skewed item degree distribution. For example, we have pages that are liked by tens or 100 million of users, and we need to handle them efficiently. On the other side, we also have, Facebook doesn't have explicit ratings for all of the pages, but we need to actually use user engagement signals in order to somehow approximate these ratings. So there are 2 common approaches for tackling this problem and solving it that are known in the literature. So the first one is item-based neighborhood models. And the second one were more sophisticated models that are based on matrix factorization technique, which is a common and well-known thing in linear algebra.
So we'll go now to neighborhood-based models, which are one of the simpler approaches to collaborative filtering. Neighborhood-based collaborative filtering starts from a set of user-to-item ratings or any kind of user-to-item scores. These could be, as Alexander mentioned, user engagement signals on pages or groups. And based on these signals, it tries to calculate the similarities between the items in order to find top most similar items for each item. And how does it go around doing that? So for each item pair that we want to calculate the similarity for, we are going to observe the set of items that were, the set of users that rated the first item, set of users that rated the second item, and set of users that rated both of these items. And we are going to use all the weights on this subgraph, combine them in some way to get the similarity between these 2 items. The simplest thing you can think about here is, let's say that this graph is unweighted, and we are going to define the similarity between these 2 items to be just the number of common users. So here, similarity between item 1 and 2 would be 3. Additionally, we might want to normalize this by the degrees of item 1 and item 2. And in practice, this graph is weighted, and we do more complex formulas like cosine similarity, Pearson correlation coefficient, or something custom to the use case we are solving. And thinking about how would you implement this, for example, in SQL or Hive, would be that you would need to join user-to-item ratings table with itself, group it by source and destination item IDs, then additionally get some global item information there in order to calculate the final item similarity scores. For some applications, we just want to get item similarities. For other applications, however, we need to calculate user recommendations, meaning we want to find the set of items that user is likely to be interested in but haven't seen them before. And in order to do that, we are going to look at every user and the set of items that he rated, and then we are going to use the result of the previous part to look at the top most similar items for each of these users' items. Now, items 4 through 7 become the candidates for recommendations for the user, and we need to find the score between user and these items in order to be able to sort them and select the top k, which we want to show to the user. Here we can put many different formulas. One example would be to sum the products of user-to-item scores and item-to-item similarities to get the final user-to-item recommendation score. Now, as you could notice on the previous 2 slides, in many stages of this algorithm, we can use different formulas to accommodate for different use cases. And we actually developed it in a way that it is easy to plug in new formulas. Parts of the formula that can be plugged in are how much a user is going to contribute to similarity of two items he rated. Then how the final item similarity is going to be calculated based on all user contributions and some global information about the items like item degree or some squared scores. And finally, how we want to calculate user-to-item recommendation score based on user-to-item ratings and item-to-item similarities. And the way we implemented this is that a piece of Java code to be used for any of these formulas can be passed through Hadoop configuration, compiled at runtime to be used for the calculation. And this is just an example how the item similarity formula could look like. So how does this problem map to Giraph? As we said, we need to map this problem to a graph. And this problem is like directly a graph problem where we have a bipartite graph where we have two types of vertices, users and items, with edges between them. In the beginning, we do some processing. We filter out low-degree users and items because they can just add noise to the system. And we calculate some global item statistics that we'll need later on for calculating similarities, like the item degrees. And then the actual computation starts where all users are going to send their rated item lists to all their items. Items receive all these lists, combine them into a map from item ID to intermediate item similarity score, and then we additionally need to get the global item information there to be able to calculate the final item-to-item similarity. Now, given the sizes of data that we are dealing with, we needed to make a few optimizations on this algorithm to be able to handle all this data. First, we made all the item information globally available, just in order not to have to request the global item information all the time and get it back, but to be able to directly access it. And for this, we used the reduced broadcast API that is available in Giraph for doing global computations and communications. Secondly, we had a problem that in Giraph, all the messages sent during a single superstep need to fit in memory of the machines. And users are sending a huge amount of data to the items. And that would require much more machines that we want to use for these jobs. So we applied striping technique, which we also successfully used in other algorithms. The idea behind striping technique is that we split the whole computation across multiple supersteps, where in each superstep, only part of vertices is active. Now, what active means depends on the algorithm itself. In this case, active is going to mean that only some subset of items is going to be doing the processing and like receiving messages and calculating the item similarities. And using this technique, by increasing the number of stripes, we can arbitrarily decrease the amount of memory that is needed for this job.
So once we have all this data computed, we can use these recommendations directly on a site by adjusting the formulas that Maya talked before. So for example, we can recommend pages that have low degree, if that's the request. Other thing is that we can provide recommendations that are based on the actual on the current user context. That means that we can recommend, for example, pages that are similar to the page that user is currently browsing, or that user recently liked. So yeah, the same algorithm can be implemented in Hive or any MapReduce framework by using simple group by and join queries. So in order to make the fair comparison here, because all of these, our algorithm and Hive, those were running on different clusters and different set of machines, we were measuring CPU processing time. So furthermore, for the Hive implementation, we had one small, relatively standard trick to optimize these queries, which is remapping all IDs to start from 1 and to be consecutive. And this way, we actually reduce the data size and as well as speed up the computation. But we actually didn't include this in the following table because that requires a pre-processing of the data. So as you can see here, Giraph implementation of the same algorithm is around 10 times faster Of course, that depends slightly on the data structure and the data size that we are dealing with here. And the actual elapsed time for the difference between elapsed time for our algorithm and Hive is even larger, just because Hive has strugglers when large item degrees are coming into computation. Again, to emphasize here that our approach is better because we deal with all of the data sets in memory, and therefore the computation is much faster instead of doing reads and writes from the disk. This slide shows how easy our framework API is to use. So here you can specify different similarity and scoring formulas, as Maya explained. You can play with the number of workers and machines that you want here and other parameters as well. So typical experimentation framework here is you try different similarity and scoring formulas, and then eventually run an A/B test to check what the best recommendations are. So as mentioned in the introduction, now we're going to move to another method of solving collaborative filtering, which is called matrix factorization. And now let's define the problem more formally. So we are given a set of users and a set of items and very big matrix, which is usually very sparse, that contains all the known ratings of users and items. So here the ratings are represented with numbers from 1 to 5. So mainly our job here is to find the missing values in this matrix. So in order to do that, one way we can solve this is that we can represent users and items with the vectors of latent features of the same size, such that if inner product of these user and item vectors closely match the known values in this matrix, then the expectation is that the inner products of other corresponding pairs will closely match the missing values in the matrix. So basically, to conclude here, now our job is actually to find these user and item feature vectors. So this is the basic form of the objective function that we are using here. So in this formula, x and y represent user and item feature vectors, and r is the known the ratings that are already provided, known ratings. So the idea here is to minimize the difference between the actual value, which is RUI, and our predicted approximated value, which is the inner product of corresponding user and item feature vectors. Because we are dealing with a lot of free parameters in this equation, we needed the regularization part, which basically prevents feature values to become very large and also prevents us of having numerical problems while doing this computation. So as finding optimal global minimum of this quadratic form is not feasible in real time, there are actually iterative approaches that try to solve this function here. So these iterative approaches usually start with the random assignments, and then we slowly move to the global minimum value by modifying both user and item vectors while iterating through all examples. So there are two common approaches. So the first one is stochastic gradient descent, which basically iterates through all known ratings in a random order. And then for a given pair, we try to modify both user and item feature vectors, move them into direction opposite of the gradient slightly so that we match the actual rating better here, so that the difference is decreasing. So alternating least squares, on the other hand, alternates between recalculating user feature vectors and item feature vectors. So at the beginning, we fix all item feature vectors, and then we try to recompute user feature vectors in such a way that they minimize these differences, but taking into account all items that user has been rated. After that, we swap user and items, and then we try to optimize for the items and so on. So both of these algorithms run certain number of iterations here until a convergence criteria is satisfied. So solution that is standard approach to this problem is modeling with the bipartite graph, as Maya already explained. So we have two types of vertices, users and items, and edges are represented as known ratings in the graph. So in order to do one iteration of alternating least squares, all item vertices send their feature vectors through the edges to user vertices, and those user vertices do a computation based on all of these messages they received, and they modify their local value. Later, users and items switch roles, and then we do the same thing for items. In order to do one iteration of stochastic gradient descent here, so in every iteration, all vertices send their feature vectors to the neighbors. So, and then for example, user vertices, they receive all items, and then they process them one by one in random order and modify local value of their feature vectors. So there are multiple problems and issues with this solution. So first of all is that network traffic is really large. So in particular, network traffic is actually proportional to the number of known ratings, which is the number of edges, times the number of features. And this is because we need to send all these feature vectors through the edges. So in order to process all of these messages, we can actually have memory problems on these machines because we need to store all of the messages in memory at once. In addition, large degree items also cause computation and memory issues simply because we need to process a lot of data for all these. So there are items who have like millions of users that rated them, and we need to process them. Finally, there is also one problem with the stochastic gradient descent, which is so this algorithm is actually not the same as the sequential one, which is running on one machine, just because we are always dealing with the feature vectors that are coming from the beginning of iteration, not the latest ones. So we had a couple of unsuccessful tries about how to model this problem better that will overcome problems that we explained on the previous slide. So finally, we decided to extensively use worker data and to extend Giraph framework and to allow worker-to-worker communication. So as Maya previously described, vertices were the only one who can actually send messages with each other, and now we allowed workers to do that as well. So in this new model, users are, again, the vertices of a graph, and user feature vectors are stored as a vertex data. But now items we store in a worker data, and worker data is actually a shared memory on every worker, so that all vertices on that worker have access to. So we're going to have a simple animation here in order to better explain what this means. So again, we have 3 workers, and yeah, we have users as vertices in the graph, and then the items are stored as a shared memory in every worker. So we needed a model here that will go through all of the edges, all of the known ratings, in such a way that every worker at some point of time gets all the items. So in order to solve this problem, we simply put all workers in a circle, and then in every superstep, every worker is processing just the items that it currently contains. And in the next superstep, we rotate the items in clockwise direction by sending worker-to-worker messages and rotating the items. So obviously, after the number of worker iterations, all workers will actually get all items at some point of time. So now we can go back, actually. Whoops. OK, yeah, this animation needs to go again. So we can go now through the problems that we had before. So first of all, the network traffic is now much smaller because the network traffic is now proportional to the number of items times the number of workers times the feature size, which is much less than in previous case. We don't have any bottlenecks on the memory because we are now processing just part of, so the whole processing thing is now distributed equally among all the workers. And large degree items do not, they are not introducing any bottlenecks for the computation as well because that's spread evenly among all of the workers. Finally, stochastic gradient descent as well is now working in the same way as in the sequential solution because we are always dealing now with the latest feature values.
OK, so Alexander described how are we going to get the feature vectors for users and items. But then, and we also know that by doing the inner product of user feature vector and item feature vector, we get the expected score for the user and the item. But in order to get the actual user recommendations, we need to find the top scoring items for each user. And this is kind of the part that is often overlooked when calculating the complexity of these algorithms. Like a simple thing we can do is look at each user item pair, compute the score, and then find the top scoring ones. But imagine that we have a billion users, tens of millions of items. This becomes unfeasible even in a distributed setting. So in order to overcome this issue, we decided to use the ball tree data structure for holding item vectors and searching the top scoring ones for the user. Ball tree is basically a binary tree where each inner node represents a ball that surrounds all the vectors within that subtree. And the leaves of this tree represent some subset of vectors. Now, there are formulas that, based on the query vector and center and radius of the ball, say what is the largest possible inner product for the query vector and any vector within the ball. Using these formulas, we can do greedy tree traversal by first going to the more promising branches and prune subtrees where we know that we can't find a better solution than what we already have within some subtree. This solution made it 100 to 1,000 times faster than comparing each pair for the small feature sizes and made it fast enough for our use cases. We have a bunch of additional features in the matrix factorization. I'll go just through a few here. So in each iteration, we track the root mean squared error, average rank, and precision recall on both training and testing sets. So users could track how the training is going, whether it is overfitting, converging, and decide based on that how to modify the training parameters. We have a way to combine stochastic gradient descent and alternating least squares. Because they operate on the same objective function, this is possible to do. And doing a few iterations of SGD, followed by iterations of ALS, and so on, proved to, in practice, give better quality of results than doing just one of these approaches. And there are other objective functions which we implemented, as well as some additions to the basic objective function. So we have a specific formulas for implicit feedback. This is like well known in literature. We have a way to add biases for accounting for users who tend to rate everything high or tend to rate everything low. We use degree-based regularization because of our large degree items. Without degree-based regularization, large degree items would start causing numerical problems. And in the future, we plan to experiment with optimizing for ranks instead of optimizing for the error on the known ratings, because that is how we eventually use the output of this algorithm. And yeah, we have a way to randomly add negative ratings, because these algorithms only work well if you have both positive and negative signal. And there isn't much of a negative signal on Facebook. That is like unliking a page is much, much less common than liking a page. And it is not clear whether that is actually a positive or negative, like whether that is clearly negative signal or the user just lost interest in something that he was interested in. And because of that, we have a way to kind of pseudo-randomly add the negative ratings while still keeping the same degree distributions of users and items. So how can we use the output of this algorithm? First, we can directly use the feature vectors that this algorithm produced in our downstream ranking models. Since these are latent features, they might not have been discovered in other feature engineering pipelines. We can use these feature vectors to get user-to-item score in real time, for example, when we need to sort some set of items for a user. Or we can use direct user recommendations to show them somewhere on the site. This graph shows how the root mean squared error changes over the number of iterations for different feature sizes. And you can see here that having a lot of iterations as well as having larger number of features matters for the quality of results, which is why having this whole algorithm perform and being scalable matters to get a good quality. So I guess you already know what the Spark ML lib is, and it has one of the leading open source implementations in the collaborative filtering area. And Databricks team published their performance numbers on MLlib in July last year. The experiments were conducted on scaled copies of Amazon Reviews dataset, which originally contained 35 million ratings. And you can see in this graph, which compares basically the CPU minutes between Spark and Giraph, that we are over 10x faster. But what is more important for us is that our solution can easily handle hundreds of billions of ratings, while the largest numbers Spark reported were 3.5 billion, so 2 orders of magnitude less. And this slide just shows how easy it is to use the collaborative filtering, the matrix factorization stuff as well, where you can play with the parameters, the tables you want to use, and so on.
And finally, to conclude, so here we presented our scalable implementation of collaborative filtering algorithm on using Apache Giraph as a platform. Our solution is highly performant as we can handle more than 100 billion of ratings in a reasonable time. And the largest known values in this field were at least 2 orders of magnitude lower. Our implementation is also easily extendable. And we presented 2 potential approaches that one can use, which is item-based neighborhood models and matrix factorization, together with actual computation of the recommendations. And proving its value, this is now used in groups and page recommendations at Facebook. So yeah, if you like this talk, a good recommendation for reading is our recent blog post on Facebook Engineering about the same topic, where you can find more implementation details. Thank you. Yep.
Yes, I do have a question, but thank you for the talk first. My name is Shang from Yahoo. For the last result, the numerical result, you show a very big improvement over the standard CF by Spark. So my question is, which Spark implementation you are compared with? Because your CF is a modified version of the CF. So is a default original CF, or also is a modified version?
So here we're comparing, actually 2 different approaches as well. So the first approach is a standard thing that was done on top of Spark. And here we are actually comparing also our new approach on our own platform as well. So it's kind of mixed thing.
So it's,
but notice that the results of these 2 approaches are exactly equal because the math behind is exactly the same. It's just that we lay out the data differently.
No, but there are 2 factors into here. One is the exactly algorithm you use. The other is the computational framework, right? So you have the exactly same input, exact same output. I understand that. But you choose a different method and run on different platform, and you just show the result together. It's not fair to say the improvement is based on which factor or is a combined result.
Well, that's not what we're trying to say. Because we didn't implement the original layout in Giraph just because we knew that it is not going to scale to our data sizes. We would be happy to compare if Spark implements the approach that we showed. We'd be happy to compare the numbers.
OK.
Yes.
Are you guys going to be looking at what happens? So you talked about negative ratings, right? And there isn't an unlike button in Facebook, or negative like button in Facebook, right? So are you looking at, or are you going to be looking at in future when someone says, I want to unfollow a page, let's say, so you stop getting that in their feed, and then when somebody actually goes and unlikes it, does that, would you think, or are you guys planning on looking at that as different levels of negative rating? And would that change the model and features in recommendation itself?
Yes, exactly. We're already using these negative signals, but sometimes it is really not clear if you unfollow a page after a certain period of time, whether you unfollow it because you're not finding that interesting right now, but you found that interesting before, which we should still use as a signal, as a positive signal, actually. So we conducted some experiments there. It is still not clear which of these approaches are working better. So we're still iterating on that.